Insufficient ground fault current can be a primary reason why a breaker fails to trip during a short circuit. The fault current may not have been high enough to exceed the trip setting of the main breaker. This can be attributed to a few factors. Firstly, high impedance in the ground path, which can be caused by a poor connection at the junction box or at the main breaker itself. Secondly, high resistance of the number 10 THHN wire, potentially due to corrosion or damage, can also limit the fault current. Another factor is the possibility of a time delay breaker. The main breaker may have been a time delay type, designed to allow for a brief surge of current before tripping. In the event of a short circuit, the fault current may have dissipated before the breaker had time to trip. The ground fault protection might also have been disabled. If the main service gear is a Siemens product, it is possible that ground fault protection was disabled through the panel settings. The ground loop impedance can play a significant role. The combined impedance of the ground path, including the grounding electrode or electrodes, may have been too high to allow for sufficient fault current to flow. Additional factors to consider include water damage. The water damage to the lighting control panel may have compromised the ground path or other components related to ground fault protection. An overfilled junction box can increase risk. The overcrowded junction box could have increased the risk of wire damage and shorting. The distance from the main switchgear is also important. The long distance between the fault and the main switchgear may have contributed to the delay in tripping. Recommended actions involve inspecting the ground path thoroughly, including all connections and the grounding electrode or electrodes. You should verify that the main breaker is not a time delay type and that ground fault protection is enabled. If possible, reduce the load in the junction box to prevent further overloading and consider installing additional ground rods or other measures to improve the grounding system. Consulting with a qualified electrician to assess the overall safety and integrity of the electrical system is recommended. When assessing the grounding system, it is important to understand the role of the equipment grounding conductor or EG. The EGC provides a low impedance path for fault current to return to the source. This low impedance path is crucial for quickly tripping the overcurrent protective device, such as a circuit breaker, during a ground fault. If the EGC is compromised or has a high impedance, the fault current will be limited, and the breaker may not trip. The National Electrical Code, or NEC, provides guidelines for proper grounding and bonding to ensure electrical safety. Section 250.4 A5 of the 2023 NEC, for example, emphasizes the importance of effective grounding paths. The code requires that grounding paths be permanent, continuous, and have the capacity to safely conduct any fault current likely to be imposed on them. Proper bonding is also essential for creating a low impedance path. Bonding involves connecting all metal parts that are likely to become energized during a fault, such as metal conduits, enclosures, and equipment frames. This ensures that all these metal parts are at the same electrical potential, minimizing the risk of electric shock. Section 250.92 of the 2023 NEC covers bonding of equipment grounding conductors. Another important consideration is the size of the equipment grounding conductor. The NEC specifies the minimum size of the EGC based on the size of the overcurrent protective device protecting the circuit. Table 250.122 of the 2023 NEC provides guidance on selecting the appropriate EGC size. For example, if a circuit is protected by a 20 amp breaker, the minimum size of the copper EGC is number 12 American wire gauge, or AUG. If the circuit is protected by a 60 amp breaker, the minimum size of the copper EGC is number 10 AWG. In the case of a short circuit involving number 10 THHN wire, it is important to ensure that the equipment grounding conductor is adequately sized to handle the fault current. If the EGC is too small, it may not be able to effectively conduct the fault current back to the source, and the breaker may not trip. Furthermore, the type of overcurrent protective device can also affect its response to a short circuit. Circuit breakers are designed to trip quickly in response to high fault currents. However, some circuit breakers may have a time delay feature, which allows them to withstand temporary overloads without tripping. This time delay feature can be useful for preventing nuisance tripping, but it can also delay the response to a ground fault. Ground fault circuit interrupters, or GFCIs, are designed to detect even small ground faults and trip quickly to protect people from electric shock. GFCIs are commonly used in areas where there is a high risk of electric shock, such as bathrooms and kitchens. However, GFCIs are not typically used to protect entire circuits. Instead, they are used to protect individual outlets or appliances. Ground fault protection of equipment, or GFP, is another type of protection that is used to protect equipment from damage due to ground faults. GFP systems are typically used in industrial and commercial settings to protect large motors, transformers, and other equipment. GFP systems are designed to trip at a lower fault current than standard circuit breakers, which helps to prevent damage to the equipment. The type of wiring method used can also affect the impedance of the ground fault path. Metal conduits, such as rigid metal conduit, or RMC, and intermediate metal conduit, or IMC, provide a low impedance ground fault path. Non-metallic conduits, such as PVC, do not provide a ground fault path, so a separate equipment grounding conductor must be installed inside the conduit. In cases where non-metallic conduit is used, it is especially important to ensure that the EGC is properly sized and installed. The condition of the electrical system can also affect its ability to respond to a short circuit. Corrosion, loose connections, and damaged wiring can all increase the impedance of the ground fault path, which can prevent the breaker from tripping. Regular inspections and maintenance can help to identify and correct these problems. It is also important to ensure that the electrical system is properly grounded. Grounding electrodes, such as ground rods, provide a connection to the earth, which helps to stabilize the voltage and provide a path for fault current to return to the source. The NEC specifies the minimum requirements for grounding electrodes. In general, 2 ground rods are required to be installed at least 6 feet apart. The resistance of the grounding electrode system should be less than 25 ohms. If the resistance is higher than 25 ohms, additional ground rods may be required. The type of soil can also affect the resistance of the grounding electrode system. Sandy soil typically has a higher resistance than clay soil. In areas with sandy soil, it may be necessary to use longer ground rods or to install additional ground rods to achieve the required resistance. The location of the grounding electrodes is also important. The grounding electrode should be located as close as possible to the main service panel. This helps to minimize the impedance of the ground fault path. The grounding electrode should also be located in an area where they are not likely to be disturbed or damaged. In addition to grounding electrodes, bonding jumpers are also used to create a low impedance ground fault path. Bonding jumpers are used to connect metal parts that are not directly connected to the equipment grounding conductor. For example, a bonding jumper may be used to connect a metal water pipe to the electrical system. This helps to ensure that all metal parts are at the same electrical potential, minimizing the risk of electric shock. The size of the bonding jumper is typically the same as the size of the equipment grounding conductor. The bonding jumper should be installed in a way that provides a low impedance path. This may involve using short, direct runs of wire and avoiding sharp bends. In the case of an overfilled junction box, it is important to reduce the number of conductors in the box to prevent overcrowding. Overcrowding can make it difficult to properly terminate the conductors and can increase the risk of short circuits. The NEC specifies the maximum number of conductors that are allowed in a junction box based on the size of the box and the size of the conductors. If the junction box is overfilled, it may be necessary to install a larger junction box or to split the circuit into 2 or more junction boxes. It is also important to ensure that the conductors in the junction box are properly supported and secured. This helps to prevent the conductors from rubbing against each other or against the metal enclosure, which can lead to insulation damage and short circuits. Cable ties and other types of supports can be used to secure the conductors in the junction box. When working on electrical systems, it is important to follow all safety precautions. Always to energize the circuit before working on it. Use insulated tools and wear appropriate personal protective equipment, or PPE, such as gloves and safety glasses. If you are not comfortable working on electrical systems, consult with a qualified electrician. Working on electrical systems can be dangerous, and it is important to take all necessary precautions to protect yourself from electric shock and other hazards. The 277/480 volt system is a high voltage system that can be particularly dangerous. High voltage systems have the potential to cause serious injury or death. It is important to be properly trained and qualified before working on high voltage systems. Always follow all safety procedures and use appropriate PPE. The Siemens main service gear is a critical component of the electrical system. The main service gear provides the main disconnect for the building and contains the overcurrent protective devices that protect the electrical system from overloads and short circuits. It is important to ensure that the Siemens main service gear is properly maintained and inspected regularly. Any problems with the main service gear should be addressed promptly. The location of the electrical system can also affect its performance. Electrical systems in damp or wet locations are more likely to experience corrosion and other problems. Electrical systems in areas with high temperatures may also be more likely to experience problems. It is important to take these factors into account when designing and maintaining electrical systems. In North New Jersey, the climate can be harsh, with cold winters and hot summers. This can put a strain on electrical systems. It is important to use components that are rated for the appropriate temperature range and to protect the electrical system from moisture. Regular inspections and maintenance are especially important in areas with harsh climates. The condition of the wiring is also a critical factor. Damaged or deteriorated wiring can increase the risk of short circuits and other problems. Wiring should be inspected regularly and replaced if necessary. The type of insulation used in the wiring can also affect its performance. Some types of insulation are more resistant to heat, moisture, and chemicals than others. It is important to use the appropriate type of insulation for the application. In summary, a failure to trip during a short circuit can be caused by a variety of factors, including insufficient ground fault current, time delay breakers, disabled ground fault protection, high ground loop impedance, water damage, overfilled junction boxes, and long distances from the main switchgear. To prevent these problems, it is important to inspect the ground path thoroughly, verify that the main breaker is not a time delayed type and that ground fault protection is enabled, reduce the load in the junction box, install additional ground rods or other measures to improve the grounding system, and consult with a qualified electrician to assess the overall safety and integrity of the electrical system. Proper grounding and bonding are essential for electrical safety. The NEC provides guidelines for proper grounding and bonding to ensure that electrical systems are safe and reliable. Regular inspections and maintenance can help to identify and correct problems before they lead to serious accidents. The type of wiring method used, the condition of the electrical system, and the location of the electrical system can also affect its performance. By taking all of these factors into account, it is possible to create a safe and reliable electrical system. Remember that electricity can be dangerous, and it is important to take all necessary precautions to protect yourself and others from electric shock and other hazards. Always follow all safety procedures and use appropriate PPE. If you are not comfortable working on electrical systems, consult with a qualified electrician.